All right, limits. So let's kind of review just briefly what we did yesterday, what we said yesterday. Okay, we talked about limits. What's a limit?
Some point where
Okay, good. So it's the ant. We'll talk in terms of the ant. That's fine. So the calculus ant approaches it, but never gets there, right? And he might get there, but that's not what the limit is concerned with, right? The limit is concerned with where does the ant anticipate he's going to step as he's taking that last infinitesimally small step, right? Remember, the ant has to be able to approach from both sides, too. Or different ants have to agree that they're going to step on the same place. We identified some places where limits do not exist. Somebody give me one place where limits don't exist. Yes, ma'am.
a large break.
Good, a large break in the function. Good. What else?
Asymptotic.
Good, asymptotic behaviors, or infinite behaviors. And then there's one weird one.
Oscillatory.
Yeah, oscillatory behavior. Yeah, that was the weird one. Okay, so then, that's all good. And we could look at pictures, and you'll get a chance to do that on the homework. Be able to identify places on a sketch of a graph, where limits exist and where they don't exist, and maybe what the values of the limits are. Next step, right? What are the ways that we can evaluate a limit? And think in math what it means when we say evaluate. Value means number, right? So evaluate means we're going to produce a number value for a limit. When we ask something like this, and we'll get to this problem here shortly, about something like the limit of x squared plus 10x plus 21 over x plus 3 as x approaches negative 3. What are the ways that we could evaluate that limit? And if I was going to say something like, if this is f of x, let's say this function, if I'm taking the limit of f of x as x approaches c, what's the meaning of that value, first of all? When we say it's the point, it's really not the point. This is the x coordinate, right? We're approaching an x value of c. What is the limit giving us back? The y value. Good. So the value of the function. We talk about a value of a function, we're talking about the y value, right? What are some ways that we could answer that question? Okay, what's one way? Say it again. I'm getting a flood of answers here. Plug it in. What do you mean? To a calculator?
Into the equation.
Okay, so we could try to evaluate directly, and that's a good plan, right? Because if it's possible, the easiest way to answer, if the function exists there, and the value that the ant actually is going to step on is the value that he thinks he's going to step on, that's easy. Plug in negative 3 and see what happens, right? That's a great way to do it. But in some cases, like this one, the answer is going to be 0 over 0, which is indeterminate. Okay, what are the strategies we have for evaluating the limit? Okay, so we could analytically, and we'll do that. Analytically is probably, that's the one we're going to focus on. That's the good one, right? That's the one that's going to give us an exact answer. Are there some ways we can approximate an answer? Graphing it, or what else? Table, right? Something numerically, either numerically or graphically, but those are weak. We're gonna focus on the analytical part, which is we're gonna do algebra and come up with an exact answer, right? So we're gonna appeal to the math gods for a real answer to this thing.
Yeah.
Let's do this one. If we try to evaluate this directly, does everybody agree? I'm gonna get what, 9 minus 30 is negative 21 plus 0 over 0. Everybody agree? Okay. So that means more work. It's indeterminate. How are we going to resolve that indeterminacy, eliminate the indeterminacy? Okay, good. We're going to factor it and try to cancel a factor, right? Okay. So this is equal to, now I want you to pay attention to to the notation that I'm using. I really don't want you guys to get lazy with the notation. I am not, vouch for me, I am not an organized person. But, you know, I mean, my garage looks terrible. But when it comes to math or physics, I am organized. And it's not in my nature to be organized, but just having done lots of hard math and physics, I learned, in some cases the hard way early on, that it's a necessity. If you don't organize your algebra and your calculus and your physics, and you're doing hard problem stuff like this, you really pay for it. I mean, it's a part of the thinking process. So you gotta, if I can do it, anybody can do it, trust me. I really want you to get used to following a rigorous notation on this. I'll just give you an example. Like, I can remember doing some stuff in college. You know, this is going to get bigger too, trust me. We're going to get into some bigger problems, but I mean, there's some classes that you'll have stuff like this too. I'm hoping. You know, you have to keep going with math and hard science and all that good stuff. In my quantum mechanics class, I can remember having a problem set where, I mean, the problems were just ludicrous. I mean, it was like problems were, a couple of them were 60 or 70 pages of just algebra. And so if you're not, you know, I mean, if you're not writing out everything in detail, it's impossible to troubleshoot that when things don't work out, right? You really have to be organized about it. So notice here that when we're doing the algebra, we haven't taken the limit yet. We haven't evaluated the limit. So this is a really common shortcut that people take, and it's a bad one. I've got to carry that limit notation with me until I actually evaluate the limit, right? So the limit of this expression is equal to the limit of this one, right? The factored form. So what's the top factor into? Right? Okay, and so now algebraically, what are we able to do? Good, we're able to cancel those. Remember what we're doing though. We have changed the function, haven't we? What have we really done there to this function?
Taken out
Good, we filled in the hole, didn't we? Right? There was a hole in the function at -3, and so by canceling these factors, we've traded this function for a simpler one, x plus 7, that agrees with it everywhere except at that one point that we filled in, right? So our strategy, and this is really cool, our strategy is that we took that function that had a hole there, which is hard to evaluate a limit, because in that case the ant is not actually going to be able to step on x equals -3. So we can't ask the question, what's the value of the function, because the function doesn't exist. We filled in the hole, so we can, right? Make sense? And then now when we take the limit, as x goes to -3, the answer is 4, right? Now we don't need the limit notation anymore because we evaluated the limit. See what I'm saying? Okay? This factor right here, and what is something divided by itself? It's 1, right? It just doesn't exist at -3. By dividing that out, we found the offending factors in the top and the bottom and algebraically canceled them. That's always going to be our strategy. It's just going to manifest itself a little differently depending on what the original problem looks like. This was a pretty straightforward rational function, right? What's that mean again? This is a little review. What's a rational function? Going back to, once again, this would be going back to probably pre-calc, yes, sir?
The real numbers.
Well, it's a rational function. I mean, it involves real numbers, but say it again. You can't have any zeros on the bottom, right? Right? But a rational function is just a ratio of polynomials, right? A rational function is just a polynomial divided by a polynomial, okay? So this is a pretty straightforward rational function. Let's look at a different kind of function. Those are pretty easy, right? I mean, you get the idea. You're just going to factor them and cancel the offending factors. Yes?
This is, I don't know if this is off topic. Where did you get the x minus 3, like the x in function, like -3? Where did
That number is, I picked that number so that it would be 0 over 0, right? Because that's just, what this is, we've got this function, right? And what this function looks like, remember, it just looks like this. We already know what it looks like. It looks like that line with a hole at -3. Agreed?
Yeah.
So, it just kind of looks like, you know, that may not be exact, but you get the idea, right? So if I had taken this limit as x approaches 2, we didn't have to do anything. I just plugged 2 in, right? And I would have gotten the answer that, whatever that value is, right? See what I'm saying? The one place where it's a little harder to do is this place, because that's the hole. That's the place where we get 0 over 0.
So whatever we make the
Well, it doesn't, I mean, not necessarily. It depends on whichever part of the function you want the ant to approach, right? I picked, because this is the one you need to practice, I made one up where the bottom goes to 0, right? But it doesn't always have to be that way. And the lesson to be learned there is, don't assume it. I mean, always try it, right? What's going to happen is, and it's a good question, and there's something I was going to tell you a little later, but I'll tell you now also, and then we'll rehearse it later again. There essentially are 3 kinds of answers you're going to get when you try to directly evaluate a limit. So if I'm given a limit and I try to plug in the value that x is approaching, one of these 3 things will happen. Either. Now the first option is, maybe you get something like, of the form, call it A over B, where B is not equal to 0. Some rational number, right? That makes sense? Maybe it could be irrational, but you get some real answer, and you're done, right? That's it. That's the answer. Okay? You could get something of the form equals A over 0, where A does not equal 0. And that is clearly a no-limit case, right? Because you can't divide by 0. That would be an example where you've got maybe an asymptote, right? So that means no limit. And in this case, you're also done. The answer is no limit. Those 2 are straightforward and easy, right? The one that we're going to focus on is the third kind of outcome. Zero over 0. And that's what we called indeterminate, and it means more work, because we have to eliminate the indeterminacy. There is another way down the road this year, towards the end of the year. I'm going to come back and I'm going to show you another technique for eliminating indeterminacy called L'Hopital's rule. But we don't need that for now. It's not, it's in many ways this is probably just as good. Okay? So we're going to focus. Is everybody okay with this? Do you agree? I mean, like if we went back to this example, like I say, if I had picked as x approaches 2, it would have been a type 1 answer. We would have gotten some number and we're done, right? If we had gotten one, I mean, like, let me give you another example. How about something like this? The limit of x squared plus 9 over x minus 1 as x approaches 1. What's that give us? 10 over, what's that mean? No limit, done. Right? Okay, Okay, but the part that is, obviously, that we're going to want to focus on is that one, right? Because that's the one where we need to do some stuff to figure out what the limit actually is. We're not done yet, right? Okay, so what about, let's try another kind. What if I gave you something like this? How about, I'll just pick this one out, but this will work. Did they not do any of those? Okay, let's try, I can make this arm to be a little shorter here. Okay. What are we going to try first? Yeah, we would try direct evaluation, but what are we going to get? 0 over 0. So we got to do more work. Okay, this one's a little tougher. There's not an easy way to really factor this. You could make that method work, but it's tough. I mean, you'd have to really be thinking ahead many, many steps. There is another way to deal with this, though. What's the problem here with resolving this indeterminacy? What's the part of this that sticks out where it's like, oh my gosh, that's hard to... The square root part, isn't it? Right, it's the square root. It's because the square root here is a part of an expression in the numerator whose value is 0, right? Right, and so, but the problem is, think what we can do. What are the tools available to us? We can't change the behavior of that function, right? Does that make sense? Like, I can't just square the top and the bottom because that changes the function, right? If my function were f of x equals x, if I were to, or let's say it was x over 2, if I square the top and the bottom, I get x squared over 4. That's a much different function than x over 2, right? We haven't just filled in a hole there. We changed everything, right? So we can't do that. So what are the algebraic options available? We don't want to change the identity of the expression, the value of the expression. So what's the identity number for addition? What's the number we could add to something and not change its identity? 0. So I could add 0. What's the multiplication identity number? 1. I could multiply by 1. That's it. Those are my options. I have to find an inventive way to do one of those things that's going to help me algebraically. Now, I want to resist the temptation to just tell you when you see something like this, you use this approach. There's going to be a little bit of that involved, but you'll forget it. That's a low level of thinking. I want you to be able to make some attachment here to a strategy too, right? So it may not come immediately, but you'll get there. Once again, the problem is we've got this square root that's involved in this expression that has a value of 0, right? We may not be able to completely eliminate square roots from the expression, but we would prefer to have, if there's going to be some involvement of a square root, we would prefer that it was part of a factor that's not going to 0, right? Any suggestions? Something I could maybe, typically we multiply by 1. There's something I could multiply the top and the bottom by that might, it may introduce another square root, but at least it's going to maybe get rid of the square root that's involved in this 0 value on the top. Do you remember anything about the behavior of square roots? Is there something I could multiply the top by so that no roots would exist in the top anymore? Okay, not reciprocal. What's the word? Not the inverse either. You've seen stuff like this before in a slightly different context. What if I did something like this? What if I have the expression a plus b? I would somehow need to get that term squared to undo the square root, right? Is there something I could multiply this by to get an a squared and a b squared but nothing else? The conjugate.
Yeah.
Right? Remember that pattern? If this term is a and that term is b, if I did something like this, I end up with only a squareds and b squareds, no a's or b's, right? You get the idea? So if we multiply through by the conjugate of the top expression, so square root of x plus 1, top and bottom, have to do the same thing on the bottom, obviously. Let's see what happens. Oh. So what am I going to get on the top? That's A and that's B. So I'm going to get x plus 1, right, which is the square root of x plus 1 squared, minus 1 squared, like that. Everybody agree? On the bottom, it looks kind of bad. You might be thinking, well, how's that help? Look, I've still got that darn square root on the bottom, but look at the value of that factor as x approaches 0. It's not 0, right? So maybe we're okay. So if I simplify this, the 1's cancel, right? I'm getting the limit of x over x times the quantity square root of x plus 1 plus 1. And now what? I can cancel the x's. And aren't those the offending factors? Those are the ones that are going to 0, right? Because x is approaching 0. See? So if I do that algebraically, now I've got the limit of 1 over the square root of x plus 1, right? As x approaches 0. As x approaches 0, I just get 1 over 2, don't I? Make sense? Okay? Try one. Try that.
So am I going to multiply top and bottom by?
Root of 3 plus square root.
Okay, everybody agree?
Oh, there's square root.
Oh, you. Okay, and so that's going to equal, what am I going to get on the top?
3 plus
Okay, everybody agree? I'm going to get the first term squared, which is going to eliminate the square root. So 3 plus x minus the second term squared, which eliminates the square root, right? Divided by x times this other factor. Well, we'll finish it up. But you get the idea. Okay, I'll throw an assignment up there, a couple assignments you can start on. I'll put due dates up, and see you Tuesday.